Okay, for question number 20, we have two students took different language facility tests. Student A received a score of 72 on the test, which had a mean of 66 and a standard deviation of 4. Student B received a score of 75 on the test. The mean was 536 and the standard deviation of 67. According to the test results, which student has a higher level of language facility? Well, since these things have different means and standard deviations, we can't just compare raw scores. But what we can compare is z-scores, and that gives us at least some possible way of comparing them. So, for the test A, we need a z-score for student A. And for that, we need their raw score for student A minus the mean for that test divided by the standard deviation for that test. And then we do the same thing for B. Okay, we get the X score, the raw score for student B, minus the mean on the student B's test, divided by the standard deviation of student B's test. So the X of B is the actual score of that student, X of A is the score of the other student, and then these are the mean and standard deviation of all students taking that test. So student A received a 72 score, but the mean was 66. So you notice that if you subtract there, you get 6. So he got scored 6 points above the mean. If you divide that by a standard deviation, which was 4, you see that that is 3/2 or 1.5. So he was 1.5 standard deviations above the mean, above average. That's a pretty good score. Okay, how about the next one? Student B scored 575 on the test. The mean was 536. If you subtract those, you get 29. That's right. 39. 39. Okay, so we get 39. So he made 39 points above the mean. But as you can see, this test has a lot more points on it. Standard deviation was 67, so you can see that he or she is less than 1 standard deviation above the mean. So this one is definitely the highest. We can go ahead and get an approximate value of that for the z-score here. I'll use a calculator. 39 divided by 67 to get a decimal approximation. 0.5821 approximately. Okay, so if you see about 0.6 here, about 1.5 here, this is the larger standard deviation. So relative to the other students that actually took that assessment, student A had the better score. Student A is more proficient because his z-score is higher, and that's the correct answer there. So the exam score is not important as much as it is how that compares to the other students. Z-scores can be used to compare two things that are different scales. Okay, next question. Consider the sample of exam scores derived arranged in increasing order. Sample mean and sample standard deviations are respectively 83 and 16.4. They didn't need to tell us that, by the way. They could have just used the actual data there, and we could have figured out the mean and standard deviation, say using a calculator. Now, Chebyshev's rule says that for any data set in any real number greater than 1, at least 100 times 1 minus 1 over k squared percent of the observations lie within k standard deviations to either side of the mean. Okay, so according to Chebyshev's rule, what percentage lie within 2 standard deviations. Okay, so Chebyshev's rule says 1 minus 1 over z squared lies within the standard, within that fraction or percentage of the data, okay, lies within the interval, okay, mu plus z standard deviations and mu minus z standard deviations. Or if you did it if it's with the sample, x bar minus zs, x bar plus zs. So z is the number of standard deviations on either side. Notice the mean is right in the middle of these intervals. Okay, so if z is 2 within 2 standard deviations, that's 1 minus 1 over 2 squared. That's 1 minus 1/4. 3/4 minus 1/4. 4/4 minus 1/4 is 3/4, which is 0.75, or in a percentage, that's 75%. So 75% must lie within 2 standard deviations, regardless of the distribution. Now, normally it's much higher than that. So 75% there is the correct answer. Now, given an exact percentage that lies within 2 standard deviations for this particular set. Notice that the first one had nothing to do specifically with this distribution. We did not need to know the mean or standard deviation or any of the numbers that are involved in this distribution. That's for any distribution. Okay, now, for this one though, we need to find this interval. Okay, so pulling our calculator back here, let's see, if we have we're on either side of the mean is 83 and it's 16.4 is the standard deviation. So we can have the mean of 83 and z is 2 standard deviations. So 2 times the 16.4. This will give us our left end, 50.2. If I do second enter and just change that to a plus, now this will give me the right end. So I need between 50.2 and 115.8. So count the things that are inside of that. Okay, so if you look, everything's inside. See, the 27's outside. Well, 27's the only one that's outside. So these are in a nice rectangle, so I can see 1, 2, 3, 4, 5 rows, 6 columns. That's 6 times 5. That's 30 numbers, one of which is out. So you have 29 over 30 is the fraction that's within 2 standard deviations. Notice that this is going to be much higher than 75%. It's actually about 96.7% if we round to 1 decimal place and make it a percentage. And that's part B. So the percentage of data that falls within 2 standard deviations is always, the choice is always greater than the percentage, or at least greater than or equal to that percentage, no matter what the data set is. There are some unusual data sets where you may get exactly 2 standard deviations. From the mean you get exactly the 75%, but that's a very unusual data set. Most data sets is going to be much higher than that. Okay, so this question here just gives a bunch of data. These are grades on a test, and we're just going to compute a whole bunch of descriptive statistics. And we're definitely going to make use of our calculators to do this. I'm going to do this on a TI-84 here to begin with. So go to Stat, Edit, and I'm going to go ahead and clear this, enter, and enter the data. Now you have to be careful that you get everything in here. 71, enter, 94, enter. I'm trying to double check these as I go along and make sure everything is correct. Can't see it, but I'm using my one finger to type in the numbers and another finger to keep my place in my list here. So make sure I'm completely on the list. I don't miss any. I'm double checking them after I type them in each time to make sure I get them in correctly. So you don't want to miss this question just because you type in one number wrong. Now the good news is the calculator will actually just compute most of these things. So really this is mostly a question on can you use your calculator to come up with some data, statistics for the data set. Now this is going to be considered a sample. So we have our data in. I believe I've got it all in correctly. Let's just double check. There's 16 here, and there's 3, 4, 5, 6, 7, 16 there, and I checked them as I went along. So I'm pretty sure I've got them in right. Now we can go to Quit, go to Stat, go right arrow to Calc, and choose number 1, and it's list 1. If you got the older operating system, it'll just say 1var stats and then L1 after it. Remember you get L1 by doing second 1. And hit calculate, and it comes up with our list. X bar is the mean, 76.4375. Okay, and I think in this one everything should be rounded off to 4 decimal places. The standard deviation, now remember it's a sample, so it's a sample standard deviation. That's the S, not the sigma. So that's the 15.024. 3 for the next digit. So everything should be rounded to, if it's not exact value before that, then round off to 4 decimal places on this question. Okay, next we have the quartiles. The minimum is 30, the maximum is 97. Q1, the TI-84 method, that's what I'm using as a TI-84, is 71, and the Q3, 86 is there. Now, let me warn you, if you use other software, you may, or there are different techniques for doing Q1 and Q3. There's not a consistent worldwide definition of what Q1 and Q3 are. So there are slight variations on the formula that could give you slightly different numbers here on certain data sets. So for example, Excel does something different than the calculator. Minitab does something different than either one. SPSS, slightly different. SAS has like 5 or 6 different choices of what you can use for this. And there's some other methods you can do it by hand that are different. But the way the calculator does it, you take the upper half, not counting the median, and do the median of that, and that's Q3. And you take the lower half, not counting the median, and the median of that is the Q1. Now, we have some other things that we need to figure out. It does give me sample size. N is 16. So those things it figures out directly. Now next I'm going to have to figure out a few things, but I do want to show you some things that we have here as variables. So for example, I'm not sure if it asked this one, but you go to Variables, VARS, go to number 5, Statistics, and I can go down to number 3, SX, and I can square that, for example, and this will be the sample variance. Because if you notice that the SX without the square is the come on. There we go. That is the number that we had for the sample standard deviation. So once you've done these calculations, of course you have to do the calculation first and then not change it but these variables will be here. So for example, if I want to find the interquartile range, okay, I can go to variable statistics, and it is, let's see, there we go. Should have the quartiles here somewhere. Let's see. Should be here. If I can find them in the list, I can just use them. There's min and max. Okay, I don't see the quartiles. Okay, so you can't do it from here, but we can still do it since we've written them down. We can do it from that. So the quartiles, Q3 was 86, and then the Q1 is 71, so you just subtract those two. So you will have to actually write those down, looks like. So that's 15. The mid-range, or the range, is you do the same thing for max and min. Now I can actually pull those out of my list here, but I've already got them written down too, so I can just do it that way. 97 minus 30, maximum minus minimum, is the range. So the range is the distance from the bottom to the top. There, 67. Okay, what else do we need to have? We probably have to do the mid-range. Okay, the mid-range is you average the minimum and maximum. 30 plus 97 divided by 2. That's halfway between the maximum and minimum. 63.5, another measure of the center. Okay, the z-score. Z-score of 81. So it's 81 minus the mean. I'm going to go ahead and use my variables for this, so I don't use any rounding off. X bar, and divide by S, which is number 3. And there's my z-score. And then round off at the end. So try not to round off any in the middle of a calculation. 0.3037. And then finally, the last one is the mode. The mode, it doesn't tell you on this calculator. But what you can do is you can sort the list. That can be helpful. So I can go over here to list, which is second stat. Then go to ops, say number 1, sort ascending, and tell it which list to sort, L1. It'll just say done. But now whenever I hit stat and edit, my list is in order. So now we start looking for repeats. It looks like there's a lot of 71s here. Let's count them. 1, 2, 3, 4, 5, 6. 6 71s. And I think you look and see there's not that much of anything else. So 71 is the mode. The mode is the most frequently occurring value. And so there is a TI-84 way of doing this. Okay, let's see if we can do this on a TI Inspire. This is the cast version, but the non-cast version works exactly the same way. So while this is loading up, let's talk about a couple things. Of course, the mean is the measure of center. That's just the regular average. You just add up all the numbers and divide by how many you have. Sample standard deviation, what you do is you take, once you find the mean first, you take each of these numbers, subtract the mean, square it, add up all those, divide by n minus 1, since it's a sample, and then do a square root. Range is maximum minus minimum. Minimum is the lowest one you have in the list. Maximum is the highest one. quartile, you throw out. Oh, let's do the median next. Put the things in order, and your data in order, and find the one in the middle, in the sense that half the data is below it and half is above it, at least approximately. Alright, let's take a look here at the Inspire. And to do the Inspire, you go to Home, and you want to select, you start by selecting a spreadsheet like this to put some data in. Okay, and which is what I have here. So I'm going to put my data in here, and unfortunately there's no getting around just typing in data. You got to do that somehow or another. 71, enter, 94, enter, and so forth. So I'm going to enter the data again. If you don't have this calculator and you want to fast forward a little bit here, you can do that. But you might want to know how it works anyway, even if you don't have the calculator, in case you ever have to pick one up and use it. Okay, so there are 16 data points. We can actually put a name in here if we want. Okay, so let's call it scores. Alright, now let's see what we can do. Let's try menu, go to statistics, stat calculations. No, I hit something I didn't mean to. Menu, statistics, stat calculations, and we want one variable statistics, one number list 1, and the list is in scores, and frequency is 1. Both of these calculators allowed us to enter frequency. If you have a frequency table where you have the x's in list 1 and say the frequencies next to them in list 2, you can choose that here. And this allows you to do some stuff with categories. We're not going to do the categories. And it tells us where we can store our results here. And here we go. And if you look right here, it has all of the things that we have here. One variable statistics, there's the mean. Okay, that agrees with what we had before. Both calculators tell us the sum of the x's, the sum of the x squares as well. Here's SX, here's sigma x. Now, use sigma, both calculators, if you know for sure it's an entire population. In this case, it's a sample, so most of the time it's a sample, so you're going to use this number here. And if you look, I believe that computed the same number. Yes, it did. N is there. Here we have the quartiles, and it's notice it is using the same method to do the quartiles. And it does SSX. That's the sum of the x minus the x bar squared. It has that value as well. And so, of course, it's that value right there that you divide by n minus 1 and take the square root to get the s. There we have the same data, the same answers on the Inspire. So it works in a very similar manner. Okay, here we have a box plot. Actually, 3 box plots side by side. It looks like we have modified box plots because we have an outlier here. And this is case prices in dollars of varieties of grapes produced by 3 different vineyards. Okay, what can we say here? Which one produced the most expensive grape? Well, the maximum of the 3 would be up here. That would be A. They also produced the least expensive too. The cheapest one, B. which one are generally more expensive? That would be B, because if you look, 3/4 of the data is way up here. Actually, all of it, but one variety here, okay, is up here. So they're generally more expensive. Which one? Let's see what else they might ask. Some other things we might ask. Which one has the most variability? Well, we can see that A has the most variability. This is a wider spread here, so the range is bigger. And that's not even just an outlier, too, so there's probably some more spread in here. The interquartile range is bigger on this as well, so we see more spread there. So each part of this is more spread. This is the most consistent, is B, although it does have one outlier here. But if you see that this part here, the upper fourth is very closely packed. This fourth is pretty closely packed. This is just a little bit less packed. And then we just got this one that's out here. So really, this is almost half the data is right there, except for that one right there, outlier. Okay. Describe which sentence describes which vineyards. This vineyard has a typical case price of about 93. Where's 93? Okay, somewhere in here. That could be, that's the median maybe. Looks like that's going to describe both A and C. So 1 describes A and C. 2, this vineyard has the most variable. That's A. 2 describes A. And the one with an outlier is B. So that was 1 is A and C, 2 is B, 2 is A, 3 is C, 3 is B, 3 is B, and so that's the one they have selected there for B. So those side-by-side box and whiskers plots can help you compare quite a bit of things about data. Two data sets. Okay, answer the following questions regarding the criterion used to decide on the line that best fits the data points. What is that criteria called, and what is the criteria? The criteria is called least squares, and what you have to do, it says that the line that best fitted data points is one having the smallest possible sum of squared errors. So what that means is if you take you're going to have a line, and given the x's that are in your data set, put them in the formula for the line and come up with the value that's on the line, on that line. But then the actual data point, the y value may be off of that a little bit. Find that difference. Square that, add up all those things, all those squares, and you want that to be as small as possible. That's how the least squares regression line works. So now let's apply that here to a problem. Okay, so here we have some data here. Okay, and this one here is, they've got a couple of lines here to try to fit the data. Maybe neither one of these is the best fit, but they're going to see which one is the better fit. And so we can go through here and work this out. So here we have the x's and y's for the original data, which are given in this table here, up here in the right, and also here in this table. And then we graph those. So 2, 4. Let's see, when you look at the scale, looks like this is going up by 2s in both cases. So there's 2, 4. Okay, we definitely have different points graphed. So let's see, 2, 4, 3, 1, 3, 0. That looks like this one here. Okay, is more like the graph. 2, 1, and 3. This one has those first 3 points right. So this one's the only one that has the point, both the point 3, 0 and 3, 1 in it. So that must be the right one. And of course you could check out the other points. 5, -1, 8, 1, that checks out. This is the line 4 minus x, so it goes, when x is 0, y is 4, so it goes through 4 there. You go the right one, you go down 1, so if you go right y2 down 2, so it looks like that. This one, when x is 0, y is 2, so it goes through the 2 there, and has a slope of negative 0.3. So you go to the right 1, you go down 0.3. Go to the right 2, you go down 0.6, and so forth. Okay, so anyway, that's the right graph. So you can look at that. Now, which one of those lines better fits the points? You might intuitively know how this works, but let's measure it using the least squares regression. So we're going to use the y-hat using this here. So using this one here, we plug in the value 2. I can do most of these in my head here. So 4 minus 2 is 2, 4 minus 3 is 1, 4 minus 3 is 1 again, 4 minus 5 is negative 1, 4 minus 8 is negative 4. Okay, so these are the predicted y's. So if you take a particular x, these will be the y's that are there. These are the actual y's over here. How far are we off? So you do the y, the actual minus the predicted. 4 minus 2 is 2, 1 minus 1 is 0, 0 minus 1 is negative 1, negative 1 minus negative 1 is 0, 1 minus negative 4 is 5. So notice that a couple of these points it went through exactly, but the others it missed some. Now these are the errors or the residuals. Now what we do is we square these. So 2 squared is 4, 0 squared is 0, negative 1 squared is 1, 0 squared is 0, 5 squared is 25, and then we add these up. Okay, 4 plus 1 is 5 plus 25, that's 30. So the sum of the squares for this one is 30. Okay, so you can remember that. We want to find the same number for the other line and compare it. So once again, we've got the same table of the actual data here, and we're going to use this one. Okay, you can do this in our head, but I can also use a calculator like this. I can do to help me figure this out. So let me show you how I could do this. 2 minus 0.3x. Save myself a little time. And I can go here. Actually, I can, what's this? I can go to stat. Well, a couple things I can do. I can go to a table and find these things in the table. 2, 1.4, 3, 1.1, 5 is 0.5, and then 8, I need to go down one more, is negative 0.4. Let me show you something else you can do. It's kind of cool. You can go to Stat, Edit. I'm going to use List 2 and List 3. So List 2, I can put my X's. 2, 3, 3, 5, and 8. List 3, I'm going to put my Y's. 4, 1, 0, negative 1, 1. Okay. Now list 4, I'm going to put the predicted Y's. And to do the predicted Y's, I want to take Y1, variables, function, Y1, of what's in list 2, second 2, and it will evaluate those like that. Now I can find the column E here is going to be the differences in these two, so I can get it to figure that out by putting it on here. And I want to do the differences is actual minus predicted, so it's the actual Y's, which were in L2, minus the predicted Y's. No, I'm sorry, the actuals were in L3. L3 minus the predicted, which was in L4. And it does those differences, so you can check that out. So like 4 minus 1.4 is 2.6, and 1 minus 1.1 is negative 0.1, and so forth. Now what I want to do for L6 is I want to square what's in L5. So I can say take L5 and square it. And of course I could have done this for the other formula as well, and I get these numbers here, and now what I want to do is add those up. And I can even get the calculator to do that. That's L6. So if I quit, go to the home screen and go to List and say, go to Math, number 5, Sum, and that was list 6 that had the sum, had the data we want to add up. And so we add that up, and it's 12.9. Now the other one was 30. So this, since 12 is 12.19 is smaller than 30, then the line B is the better of the fit. Smaller sum of the squares. Now here we can find a regression line, and this, to do this regression line, we're going to use our calculator again. So here, let's go in, and for our let's do this, use list 1 and list 2. So we go to Stat, Edit. Okay, I'm going to go back here. I'm going to clear list 1 and clear list 2. I'm going to clear list 3 while I'm at it. Don't really need to, but okay. So let's use list 1 and list 2. List 1, I'll have my x's, 5, 3, 1, 4, and 2. 1, 4, and 2. And corresponding y's are 9, 2, 0, 3, and 1. And so now you see here that you have the table of x and y values in L1 and L2. Good time to double check these. Make sure you have them in correctly. Okay, looks good. Now to find a regression equation, you quit and you go to Stat and Calculate. Now you have actually different models for regression, but number 4 here will do what we want, linear regression. The x's are in list 1, the y's are in list 2. No frequencies. We're going to store our regression equation in y1. Now, if you have the older operating system, it will just look like this. Linear regression, and you give it L1. Actually, I don't think it has the parentheses. It may say AX plus B or something, but you give it L1, L2, Y1, and again you get Y1 by variables, Y variables, function 1. Okay, moving back to where we were. Now we calculate. Oops. Problem. That's should be okay. What's wrong? Got the same number. You have to have the same ones here and there. Linear regression, L1, L2, Y1. Data type. It did it then. I'm not sure why. Maybe I needed to clear. I shouldn't have done that, but I cleared out the y equals on the y1, and then it did it. I'm not sure why it did that. Now yours may or may not have these r values. If you'll do this just once, go to Catalog, go down to the D's, and go down to Diagnostic and turn it on. You only have to do this once. Turn the diagnostic on, hit Enter. Now let's do that regression again. Stat, Calc, number 4, list 1, list 2, put our regression equation in y1. Some of you may have a newer operating system. If you do, the shortcut is alpha trace, which is F4, and you get Y1 faster that way. For some reason it is not letting me do this when I already have an equation in there. So clear that out first, and then run it. Okay, so it's telling us the formula is the form y equals ax plus b. A is the slope, 0, b is the y-intercept. In this case, a is 2, b is -3. And these things here are measures of how well they fit. So the r² value is something that's between 0 and 1. If it's 1, it's a perfect fit for all the points. If it's close to 1, it's a really good fit. The r value is, of course, the square root of the r² value. It's always between -1 and 1. If it's positive, then you have a positive slope, and closer to 1 or -1 is a better fit. Closer to 0 is not as good a fit. If it's a negative value, it's a negative slope. So, doing that, that's our regression equation. So it's -3. Let's see, it's 2x minus 3. So here they've written it as -3 plus 2x, same thing. And then we can graph that along with the points, and now here's how you can graph it on your calculator. Okay, go to stat plot, go here, turn it on, go ahead and turn on the stat plot, make sure it's the dots. My x's are going to be in list 1, my y's are in list 2, and I like to use the little box. And then we do zoom. Number 9 is zoom stat, so I'm just going to type in 9, and it automatically produces a window, and then it does the graph as well. So then you can see which one of these looks the most like it. So certainly we can eliminate A and C because they have negative slopes. So then it's either B or D. Okay. Well, the line has a negative y-intercept, so that's going to be B. Plus the data points are arranged a lot more like that than they are here. So there is, we could check every other details, but B is going to be the answer there. Okay, so again, this one is a linear regression problem. So here we have this, we have our years, and we have our populations. So we can do a similar kind of thing here. I'm going to first go over here and clear that out so I don't have that problem again. Go to stat and edit. Again, I'm going to use list 1 and list 2, so I'm going to clear them out like this. List 1, I type in the data. Now, if you want, you can let x be the number of years since a certain year, but I'm going to actually use the actual year numbers. For linear, this usually works pretty well. And unfortunately, there's no getting around just typing in the data. Oops, that one's not right. Okay, and then now we type in the data. So X is the year number, Y is our data, which is, what is it here? It's population in millions of people. So the units are millions of people for the y's here. Okay, so we have our data in. So now if I quit and do that, now I can, let's graph it. So again, I go to, my stat plot's already actually set up for list 1, list 2. So if I just do a zoom 9, it will graph it. Oh, this looks like a very linear or nearly linear plot. So a linear model would be a very good model for this. So let's have it calculate that. So we can quit and do stat calculate. We want to do number 4, linear model. It's already set up for me. Put my regression equation in list 1. And calculate that. Okay, so this is my model here. If I need to write my formula down, it is 3x minus 5718.9. And notice we have an r squared value 0.998, r value 0.999. That's a very, very good fit. If I hit graph now, it will graph it because it put the formula in for y1. So if you need to read the formula again, you've got it there. You don't have to run it again. Okay? Now that I have the graph, I can trace on the graph and look ahead or behind. So 2010 and 11 are the next 2 years. It wants to make predictions for those 2 years. Now, if I wanted to see it on this screen, I need to make sure my window goes there. So let's see, let's start at 1988, a couple years before our data, and let's go at least, let's go 3 or 4 years out in the future. So let's go like 2014 or something here. So I can change that a little bit. If I do that, it's increasing. I may want to increase my max just a little bit. So let's leave that about 240. Let's go up to about 340 here. That's 100, so maybe I want to mark that off in tens. Okay, now let's look at the graph. Okay, that's a pretty good look at our graph. I can do trace and type in the, now notice if I trace here, I'm tracing points that are actually on the data points, but if I use my up or down arrows, now I'm tracing predicted points on the y's. And I can type in the number 2010, and it'll go straight to that point on the curve. And so it's 311.1 million, 311.1 million people, 311,100,000, 311,100,000 people. And now I can type in the 2011, and then I'll go to the next point. It shows me where it is, and it's 314.1. Or I can go to table setup and tell it to do it as an ask table, and then go to here and type in the X's that I want, 2010, 2011, and we can do that. We can also do it from the home screen. We can say take Y1 of 2010 and then Y1 of 2011. So, several different options about how we can get that. Of course, we could just plug it in by hand using that formula. Okay, looks like this is, the last question on the assessment here. Our example problems. A survey of car rental agencies shows that the average cost of a car rental is 33 cents per mile, standard deviation of 4.4 cents per mile. Assuming we know nothing about the shape of the distributions, which of the following says something about the proportion of the data close to the mean? That would be Chebyshev's theorem. The empirical rule only works if your original data is normal. is normally distributed, or at least approximately normally distributed. What percentage must be between 20 and 46, okay, cents? Well, we need to figure out z-scores for those. Okay, so the mean is 33 cents per mile. The standard deviation is 4.4 cents per those should be the same units. I'm going to say cents per mile. Those should be the same units. Something's wrong with that. Standard deviation should be in the same units as your x units. So I think this is cents per mile would make the most sense here. Okay, so we need to find the z-scores that go with 20 and 46. So 20 minus 33 over 4.4. Let's use my calculator there. 20 minus 33, because you put that in parentheses, divided by 4.4. That's a z-score of negative 2.9545. Looks like 45 repeating. Okay, and then the other one is 4.4. I'm sorry, that's the standard deviation. What's the other score? 46 cents. 46 minus 33 over 4.4, and that's a z-score. So there's z1, z2. So I can just do second enter and change the 20 to 46. And that's positive 2.9545 repeating. Okay, so this is the same absolute value of z. And so what this says is, so between these two z-scores, so Chebyshev's theorem says if you're within this z standard deviations of the mean, you must have 1 minus 1 over z square of the data. So we need to compute this. So it's 1 minus 1 divided by my previous answer squared. And this is the decimal version of what's there. So if that rounds off to that's 88.5 something percent, rounds off to the whole percent is 89%. Find an interval that guarantees at least 84% of the data. Okay. Well, again, we're using Chebyshev's theorem here. Okay. So we know that Chebyshev's theorem says 1 over 1 minus z squared is of the data, at least, guaranteed at least this of the data is in the interval x bar minus zs to x bar plus zs. So at least that percentage, at least that fraction is in there. Okay. Now so in this case we have 1 over 1 minus z squared equals that fraction of percent. In this case we know that's 84%. Well, first thing we do is change percents to decimals to work with them. And so what we're doing is we're solving this equation. So if we subtract 1 from both sides of the equation, we get negative 0.16. Now multiply both sides by negative 1. 1 over z squared is positive 0.16. Now reciprocal both sides. Z squared equals 1 over 0.16. And so z is the square root of 1 over 0.16. Again, I can use a calculator, so I might be able to do this in my head actually with a little bit of manipulation, but let's do it with the calculator. 1 divided by 0.16 and this is going to be my z-value. Z is 2.5. Okay, now, then we need to figure out, that's the z-value, and then we need to figure out this interval. Okay, so in this case, x bar was, so 33 and 4.4 are the numbers. So x bar is 33 and s is 4.4. So we do x bar minus zs to x bar plus zs. So that's 33 minus 2.5 times 4.4. That's the lower end of our interval. And notice the 33 is going to be right in the middle here, because we're adding and subtracting the same amount. 33 this is where you can see it better, plus 2.5 times 4.4. Okay, so let's figure out what those two numbers are. So we have 33 minus 2.5 times 4.4. That is 22. And same thing, but change that to a plus instead of a minus. Add instead of subtract, and we get 44. So notice 33 is exactly halfway between 22 and 44, and if we go 2.5 standard deviations above and below that mean of 33, we get 22 and 44, and within 2.5 standard deviations we're guaranteed at least 84%. So 22 and 44 are the answers. So hopefully that will give you several problems that you can use to study this and review, and you can see how some of the questions are done in this unit. And for my classes, this is actually going over the practice test, which was one of the graded assignments. Hope you'll find this video helpful.